All right, welcome to Mr. Strauss's Chemistry Corner. I know it's been a long time since I've made a video, so I just say przepraszam to my Polish friends out there, and guten Tag to my German followers. All right, so we're going to be looking at quantum mechanics and the Bohr model of the atom. And last model of the atom we had was the Rutherford model, and good thing about the Rutherford model, it predicted the nucleus. Bad thing about the Rutherford model is it didn't explain why the positive and the negative electron aren't attracted to each other, and they didn't explain what created those spectral lines. So remember when we looked through the spectroscope, we saw purple, blue, green, and red for hydrogen. Okay. So Niels Bohr came up with a solution to explain those spectral lines. And basically, he was thinking along the lines of Max Planck, in that if light can be quantized, if you can think of light as these tiny little packets of energy flying through the air, why can't other things be quantized? And so Niels Bohr said, I believe that the orbits themselves are quantized. That we've got the nucleus in the center, but then going around them are very specific orbits. So when I mean specific, at certain distances and no others, quantized. And that those orbits will continue going on and on and on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the way to infinity. Okay. So those will just keep going and going and going and going. So you don't have to. Oh, now let's write this on there now, I suppose. So let's put the energy level and their corresponding energy, so the level and their energy. So the first energy level has an energy of negative 1310. The units are kilojoules per mole. Second energy level, negative 327. Third energy level, negative 145. Fourth energy level, negative 82. Fifth energy level, negative 52. You don't have to memorize those numbers. Those will be given to you on the test, but it's nice to have them up here to refer to while we do the problem.
What's the unit code?
Kilojoules per mole. Okay. So you don't have to write down this analogy, but suppose I want to measure the height of a mountain. Where will I measure from?
Base to the top.
So normally you start at the base and we say it's 0, and you measure up to the top of the mountain. Okay? That's one way you could do it, but that's not how you have to do it. You could say the top of the mountain is 0, and then you can measure down. Okay? The total difference is still going to be the same, 1310, 1310. It's just a matter of the sign. So you could measure from the top of the mountain down, and you'll get the same overall change. So that's what they did with the atom. They said at infinity, the value is 0. So at infinity, there's 0 energy. And then everything is measured off of my 0 point, which in this case is at infinity. So if my electron falls from infinity all the way down to the first energy level, it's going to give off 1310 kilojoules per mole. If my electron falls all the way down to the second energy level, it's going to give off negative 327. So if you don't fall as far, you're not going to give off as much energy. Okay? No different than my mountain analogy. If I fall the whole distance, I fall 1,310. If I only fall some of the distance, I'm going to give off less. The less distance I fall, the less energy is given off. Okay? Does that make sense? Questions? All right, let's do a problem then. How much energy is released when 1 mole of electrons fall from the 4th to the 2nd energy level? So how much energy is released when 1 mole of electrons fall from the 4th to the 2nd? If I start going too fast, please let me know. So here's my electron in the 4th energy level. It's going to fall to the 2nd. When electrons fall, they're going to give off energy, so we want to find out how much energy it's going to give off. And to do that, very simple equation. The change in energy is equal to the final minus the initial. Always final minus initial. So the final level is the 2nd. So when I look at my values here, negative 327 is the final, minus the initial, which is the 4th energy level, which is negative 82. So you're subtracting a negative, so that's going to be adding, and that comes out to be negative 245 kilojoules per mole. So now how is that energy going to be given off? Is it going to be given off as heat? Is it going to be given off as motion? Kilojoules is the measurement of it. So it's going to be given off as light energy. So now the next part is what wavelength of light will be produced. So the other equation we've got is E is equal to hc over lambda. That's the one that relates energy to wavelength. If I do a little algebra, wavelength will be equal to hc over E. So I know H, I know C, I'm trying to find my wavelength, and my energy is this number right here. So my wavelength is equal to my Planck's constant, and yes, Planck's constant can be 6.626 times 10 to the negative 34th, or
Oh, it's 1 mole.
if we're dealing with 1 mole of something,
3.992.
then we're going to want to use the 3.99. So 3.99 times 10 to the negative 13th kilojoules times seconds per 1 mole. Multiply that by C, which is the speed of light.
No, times.
And then we're going to divide it by the energy. Okay. Now, delta E is not the same as E. We have to turn delta E into E. And we do that by taking the absolute value. So the absolute value of delta E is E. Basically, we're just going to get rid of the sign. So when I plug in for E on the bottom here, it's not negative 245, it's just 245. So that gets rid of the negative sign. And then if I plug it into my calculator correctly, I get 4.89 times 10 to the negative 7th meters, or 489 nanometers.
Is it meters a second?
Nope, just meters, because if you look at the units,
Meters a
kilojoules cancel with the kilojoules, moles cancel with moles, seconds cancels with second. The only unit left is meters, and wavelength should be measured in meters. But that's, again, that's an important thing to do, is always check to see that your units are being canceled. And then on Appendix I, it will tell you the type of light being produced. So you're going to want to use your appendix. And if your wavelength is 100 meters, you've got radio waves. If your wavelength is about 1 meter, radar. If your wavelength is between 100th and 1,000th, microwaves. And if your wavelength is to the negative 7th, then you're looking at visible light. And in particular, (400 nanometers to 700 nanometers). And if we're at 489, that puts us right about there. So what type of light is being produced? Blue light.
Wait, but what appendix is this?
Appendix I.
Oh, okay, so
So when the electron falls from the 4th to the 2nd, it is going to give off blue light. No other color, just blue. 1/4 to the second will give off blue light. And so Bohr had explained what's creating these lines. So when an electron falls from the 1/4 to the second, that's what's making the blue light. Okay? What he had trouble with in the beginning is, why are those orbits quantized? Why can they only orbit at certain distances? Because planets don't do that. Things in everyday life, if I'm swinging a ball over my head, the ball can orbit at any distance. It's not like I can only swing it 1 foot, 2 foot, 4 foot, 8 feet away. It can be at any distance. But electrons can only be at certain distances, certain quantized orbits. All right? Any questions? Yep.
So the 3.99 to the 10 to the 13th power,
Yep.
what's that?
That is Planck's constant in kilojoules per mole.
So that's standard in every single.
Yep, Planck's constant is a
Alright.
constant. Speed of